This is what my voice, and this is the different presentation of the voice. Fourier, wavelet, continuous wavelet, and HHT. As I said, the HHT gives you a very, very detailed structure compared to all the other three. In fact, HHT, you can treat SHT as a magnifying glass to look at the details. Not only you can look at the details of each frequency band, but within each band, there are also structures that we can see. HHT is not only good for looking at the detail, it is also good for looking at the trend. For example, we're going to talk about, I give you this example of a global temperature anomaly from 1856 to 2003. This data set starts from, as I said, 1856 all the way to 2003. Each point is 1 year average of global temperature anomaly. Now, this sudden sharp increase is treated as primary evidence for global warming. Yeah. But you notice that the change is not monotonic. It's always going up and down, up and down. Okay? And around this time, in the 60s and early 70s, the newspaper is not talk about global warming. It's talk about going into ice age at that time. Somehow after that, we'll talk about global warming. For this kind of data, if we do the empirical mode decomposition, we are going to get the last one is actually a trend. So this method is also very good at the trend. And we're going to talk about the trend later in detail. Here, we just tell you that not only we know which components are important, these are the significant tests that we're going to cover again in the lectures. And for that, we will find out this trend actually is not, this is a monotonic trend. This is an overall trend. There are many different trends. When we talk about trend, we'll give trend a very good definition. Trend is not something that you can draw a straight line and forget about it. Okay? And if you draw a straight line, the slope is constant. That means the increasing of temperature is a constant rate. If you draw a curvilinear trend, and so your increase rate is not constant, we're increasing much faster here than here. In other words, at the beginning of the record, the increase, we still have increase, but the increase is much slower. So with this method, we can not only talk about the large structure, we can also talk about the small structure. Now, what does this mean? I give you all this example, not just try to teach you the method right now. I just give you this example to illustrate my point. The point is that the instantaneous frequency actually offer you a very, very different view of data. Instantaneous frequency is of critical importance. It is not that we can find a wave and say, well, I know the period, 1 over the period is the frequency. That's not enough. Not anymore. Yeah. For our study, we do need a frequency that is a function of time. And how can we get that frequency as a function of time? Fourier does not give you that. Okay. If you use other methods, like short-time Fourier, does not work. And if you look at, say, wavelet do give you a frequency as a function of time, but it's integrated over a period. So with this instantaneous frequency, we don't need the harmonics anymore. The harmonics, when I present you the example, the harmonics is actually you need, once you adopt a priori base, then that base does not feed your data very well. Then you need another time to get rid of the residual. The base you define. however cleverly you define, will not fit all the data. So Fourier, the first component gives you the first order approximation, the second order approximation. So all the harmonics are because you have an a priori base. If you have a Fourier, you have Fourier harmonics. If you have wavelet, you have wavelet harmonics. But if you use HHT, you don't have harmonics. The harmonics is something that you need to fit the specific waveforms. Yeah. If my wave is a sine wave, of course Fourier works very well. If my wave is not sine wave, then you need many components of Fourier to fit the the waveform. And not only we don't need harmonics, we also do not have the uncertainty limitation like in the speech analysis. Why we have the uncertainty principle? Because we use integral transformation. If you define a priori base, that's the only thing you can use. That's the convolution analysis or the integral transformation. So with this instantaneous frequency, we can define frequency by differentiation. And that is a very different approach to data analysis. Now, how can we do this? We can do this because we have adaptive basis. This adaptive basis is not a priori defined. Not that you have a base that is I have a base. Now give me your data. The base the base for the data is defined only after we see the data. So this is totally data driven, if you want to use that word. But this adaptive base is extremely important. It's the key. This adaptive data can give us a detailed analysis of nonlinear data from nonlinear process and the data from non-stationary processes. Yeah. Because of this, two differences, I think that HHT established a total new approach, new paradigm for data analysis. Yeah. This is the key that I want to emphasize in this class. And to summarize the differences, we have everybody know Fourier, and most people know a little bit about wavelet. And here we want to talk about Hilbert. The difference is that the base is adaptive, not a priori. In other words, we do not define base before we see the data. The bases are defined based on data, so it's totally adaptive to the data set that you give me. And because of that, the frequency is determined not by integral transformation. For Fourier, integral transformation is from minus infinity to plus infinity, or capital T, minus capital T to large capital T. That's your total data length. So that frequency is defined globally. That each frequency is constant over the whole data range. Now, if you go to wavelet, the wavelet changed. Wavelet, the integration is not to the whole data length. The wavelet data is integrated to that particular mother wavelet or whichever wavelet you define. So it's regional. But nevertheless, they still use integral transformation. Therefore, there's still uncertainty limitations. Here, our frequency is defined by differentiation. Time derivative of phase is our frequency. So time derivative, how local can you be? When you calculate the differentiation, you need 2 points to the limit. Yeah. Occasionally, we're not that local. When we talk about instantaneous frequency, you'll find that we do use a little bit more points to make it smoother, because sometimes the data is very, very rough. Anyway, so integral and differentiation, that's the difference. Yeah. And then once we have the data reduced into local frequency, and we have local amplitude, then we can really construct the energy time frequency presentation rather than like a Fourier, like a energy and frequency presentation. So we have time frequency analysis, a real time frequency analysis. And we can do nonlinear data, we can do non-stationary data, we don't have uncertainty principal limitation, we don't need harmonics. Yeah. Harmonics, as the example that I repeatedly shown you, that it's not physical, it's mathematical. So we can almost draw a conclusion to the introduction now. The introduction is that the adaptive method, I think, is the only scientifically meaning way to analyze data. Any other way is also meaningful, but mathematically. Yeah. You use Fourier. Fourier is very nice, and actually Fourier is very powerful. After I repeatedly compare with Fourier, I found that Fourier is very, very good. Nevertheless, it does have those shortcomings as I summarized. Another thing is that the only way to find out the underlying physical process, you have to use adaptive method. You have to use adaptive basis. Therefore, it's indispensable for scientific research. Scientific research is not just grinding through the data. Scientific research is finding the physical meaning of the data. Yeah. The physical meaning of the data is embedded in the data. The physical process is embedded in the data. If you analyze the data, you should be able to learn something about the processes. And the method that I would cover in this class, in this course, is very physical and very direct and very simple. Yeah. So HHE looks wonderfully simple. When I made this view graph, I've been juggling around the word. I have tried to say that the HHE is simply wonderful, or wonderful and simple. But I want to emphasize simple. It is really simple. Yeah. Having emphasized the simple, I have used a but. The devil is in the detail. This introduction, I have used more than 2 hours to give you introduction. I want to give you an overall picture so that when I talk about the method, you know where we're going. This is an overall map. Okay? And this method, from the surface, looks so simple. I remember when I first developed the method, I went to a university to give a talk. And after the talk, they asked me to stay for another day to discuss. So the next day, after the talk, next day, 2 faculty members come to me and say, we've already done the HHT, not HHT, the empirical mode decomposition. So they present to me some of the sampled data. It works all right, but they didn't know there are lots of little details hidden in there, like the N effects and like how to compute the frequency and so on and so forth. Not for a model data, but for real data. The real data is so highly variable. So every day, I still encounter frustrations that are of the problem that I cannot solve because the details. So this course, the whole course of this is to discuss the details. Yeah, the overall roadmap is clear now. It's a very simple method. It's very direct. But how about the details? So this will be our course. Our course is, we have finished the introduction. The next time we're going to talk about EMD, talk about intermittency, talk about the ensemble EMD, orthogonality, and the effects, relationship with Fourier analysis, trend and detrend, as I have already presented. And we have to talk about the Hilbert spectral analysis, give you a little bit of mathematical preliminary. And even in Hilbert transformation, we still have N effects. So N effects is going to be with us all the time. Yeah, we have to deal with those end effects. And we'll talk about wavelet and compare with Wegener-Weil, and then instantaneous frequency is our important thing. Then paradox of instantaneous frequency. To this day, there are still people don't believe instantaneous frequency, and they propose many, many different difficulty points, try to say refute the definition of instantaneous frequency. We're going to talk about that, and then we'll talk about the marginal spectral analysis. And then we'll talk about the multidimensional EMD. Now we have time frequency analysis for time series. And how about the image? How about other data? Then finally we'll talk about applications. Yeah. I hope in this course we'll at least cover some examples of application so that you know how to use it in a real problem. And here's the history of the method. The method was formally introduced in detail in a paper in Proceedings Royal Society in 1998. The paper was submitted in 1996, but the paper is kind of too long. The Proceedings of Royal Society at that time had a hard time to print the paper that long. This paper is about 100 pages long, 93 pages. So the paper was actually accepted in 1996. It took 2 years for us to help them to get the paper in print. I've redrawn all the figures to fit their machine. Finally get it published, and then I have another paper immediately following that. It's in the annual review of fluid mechanics. The annual review in fluid mechanics is basically recap this method. A review paper usually is a review some subject which has been there for a while. But since the method was finished in 1996, a few of the annual review editors know about this method. They are eager for me to write a review article. So they asked me to write a review article. I accepted because that's a big honor, review article. This annual review has lots of people read those papers. I accepted, but I waited until 1998 to have this paper. If you want to review some paper, the paper should appear. You cannot review a manuscript, right? So I waited until 1998. The paper only appeared that year. Then 1999, they will have to publish the review article. So this is probably the shortest period between the paper and its review. The review was done, in fact, the year following the publication of the paper. But this paper has been cited many times. This is probably the second most cited paper that I have ever authored. And then in a few years later, I'll talk about the confidence limit. That is only one of the confidence limit that we can do. There are many, many different ways to define confidence limit. We'll talk about that. And then in 24, this is not impress anymore. I should change that. We studied the characteristic of white noise. From the study of white noise, we get into the ensemble EMD. We talk about the EMD, we're going to talk about the ensemble EMD, what that means. And and then we did this trend, D-trend in last year. We try to tell the community that drawing straight lines or any function as a trend is not reasonable. Yeah, how to define trend and how to take the trend away is what we discussed this. And in fact, after I left the United States and come back here in 2006, I've made a decision not to publish any paper in other journal anymore. This is one of the exceptions that I made. From now on, you're going to see a lot of paper appear in the advances in adaptive data analysis. Yeah, like the ensemble empirical mode decomposition, it's appeared there. In fact, this paper should appear in 2009. But I have already seen the Gallup proof of this. This journal is a new journal that I initiated. It was supposed to start in 2008, but the change in personnel and all the other complications delayed it. Okay, so it will come out probably shortly, maybe this month or next month. It should come out. This paper you can download it from the NCSU website. I think I have put that on there. Then following that is instantaneous frequency. This is the subject I'm going to cover in our course. And we're going to talk about the multi-dimensional ensemble empirical mode decomposition. And that will also appear in this journal. And this paper is already accepted. But the reason that at the request of the collective author of this paper, we have to delay publication of this because of the patent issue. Yeah. I hope after I present this, a year later or 2 years later, you can throw away the notes. We'll have a complete new notes. The reason is that I do know my limitations in mathematics. I have criticized the formal mathematical approach to data analysis. But deep inside, I do understand that mathematics, a famous Chinese mathematician Chen said, mathematics is useless. But without mathematics, you cannot do anything. So mathematics is important to make sure that we don't make colossal mistakes. So ever since I developed the method, I've always looked for mathematicians to help me. Yeah. So any department of mathematics asks me to give seminar, I always show up. Yeah. I always challenge them with this new approach, the new way of looking at the data. There are two places that I particularly worked hard on. So one is Princeton University, the other one is Caltech. Yeah. The Princeton University math department is one of the top math departments. And they have, of course, they have many mathematicians, but they may not be interested in the method that I developed. One of the professors there that I think can be of particular help to me is Professor Ingrid Daubechi. Yeah. If anybody has played with wavelet, you should know Ingrid Daubechi. Wavelet has each wavelet has the so-called mother wavelet. Yeah. I give Ingrid a nickname which I call her in front of her face is not mother wavelet. She's the mother of wavelet. Wavelet was a method that people used without rigorous mathematical structure or mathematical proof. Ingrid Daubechi, in her book in 1992, SciEm published 10 lectures in wavelet, lay a rigorous foundation for wavelet, especially for discrete wavelet. Yeah. So with that, wavelet becomes the mainstream of math. So now you go to wavelet meeting, you see a lot of mathematicians talk about wavelet and generalized harmonic analysis. So I have always think that she should be the person that can help me the most. So about 10 years ago, I first showed up in Princeton math department and give the talk. And at the very beginning, I started to talk about how bad wavelet it is to analyze data. And Ingrid stopped me. Says Norton, let's don't talk about the shortcoming of wavelet. We all know the shortcoming of wavelets. we have to see how your method works. So I made a presentation, and I think gradually I sort of convinced her that we do have some very, very different point of view in HHT or EMD. So we agreed to work. And we agreed to work actually 5 years ago. We wrote a proposal to NASA, and NASA turned us down. NASA said, "Oh, this is not a wavelet. We don't need this." Yeah. So sometimes the manager is very difficult to deal with. But fortunately, last summer when I went back to the United States, we wrote another proposal, and this time it get funded. Yeah. And this will be for mathematics study, be a pretty sizable proposal. That Ingrid Daubechies will be the principal investigator. I will be the co-principal investigator for the next 3 years. Yeah. I hope by the next time or the time after next, I will present a totally different view, because the whole study is to establish mathematical analysis of empirical mode decomposition. I hope there will be some rigorous mathematical definition for everything we are doing here. That's my hope. However, seeing what the Fourier analysis went through, yeah, it'll have to wait 130 some years to get a full proof. Back in my mind, I also have the thought that maybe the proof will not come so soon. Yeah. Anyway, so this is the latest, the most recent development that we have in the HHT. As I said, I have zeroed in on 2 places. Ingrid Daubechies is the director of applied and computational mathematics at Princeton University math department. Dr. Thomas Ho is the director of applied and computational math at Caltech, California Institute of Technology. Yeah. I'm working on him. I said, well, listen, there's a new method that we ought to work on, and year after year, and finally he was convinced. So he joined me in editing these advances in adaptive data analysis. And this will talk about theory and applications. Yeah. So the volume 1 should come out shortly, even though it's January 20th. It says 2009, but it will come out shortly. Yeah. So this is in a way is an advertisement. If you have any more paper that you are working on with the adaptive method, you don't have to use HHT. Any other adaptive method counts. So this is advances in adaptive data analysis, not just any data analysis. Yeah. So if you have papers, you consider this journal. We are going to pull all the paper together to so we have a forum, we can talk, we can discuss, and we can advance the methodology and understand the data. Then people may think, say, hey, you don't have a mathematical foundation yet. Why then you keep teaching this method? As you can see a few view graphs ago, this is our opening statement in the proposal. Yeah, since its invention over 10 years ago, this has been applied to a wide range of application, and it's remarkably successful and useful. This is a useful method. Yeah, even though we do not have the complete theoretical data, I suggest that we look at it, we use it. And to justify that approach, I quote Oliver Heaviside. Oliver Heaviside is one of those, the word maverick, yeah, is very different. He invented the step function and delta function. When he introduced this function, people laugh at him. He said, listen, that function is not even uniquely defined. Delta function, for example, is defined as a function has an infinite big value at 0 and the integral and infinite point at 0. The value is very high and the value is 0 everywhere else. And the integration of that, however, is unit. And mathematicians come out all kinds of different ways to define that function. So they make a joke of him. This method is not unique. It's no good. We shouldn't use it. It's not mathematics. It's pseudo mathematics. Yeah. But some of the physics really love the method, but some of the mathematicians really attacked him pretty severely, and it's so severe that he has nervous breakdown. He finally was committed to the institute. Yeah. But he said something, I think it's interesting. So I quote what he said. He said that, why should I refuse a good dinner simply because I don't understand the digestive process involved? In other words, the biochemistry of digest a good dinner, it's still not totally clear to us. But do we eat dinner? Yes. Yeah. So this is the same philosophy that I have. Our engineering scientists, we don't want to be totally unreasonable. Yeah. We'll be reasonable to a limit, but we'll not go to the last couple inch to have a totally rigorous proof. And that we have to wait for the mathematicians. Yeah. So here, the mathematicians from Taida and Jingyi, you have to work harder than us, try to establish the mathematical foundation for this. Because with or without that, we're going to use this method anyway. Yeah. So currently, having that philosophy in mind, I've been applying this to all kinds of problems. Some of these examples I will share with you when we talk about the applications. Yeah, we'll do non-destructive evaluation, structural health monitoring. That I did it with Department of Transportation in United States and the Naval Surface Warfare Center in United States. We've done the NASA for shuttle, and we are now negotiating with Taiwan high-speed rail system. Yeah, and we did the vibration speech analysis with FBI and DARPA. DARPA is Defense Advanced Research Program. That is in United States, it's a hush-hush establishment. It's do research for the Department of Defense. And the size of that is bigger than National Science Foundation. Yeah. Their budget is key to defense spending. So every $100 defense department spent, you have put aside $1 for research. So the year that I left the United States, the Defense Department spent $400 billion. So they have $4 billion budget. National Science Foundation has less than that. Yeah. So they are very, very rich research family, research organization. Earthquake engineering, biomedical application. Ever since I come back to Taiwan, this is the area that I devote most of the time thinking about it, because the research center that I established, 80% of the faculty, that's 4 out of 5 faculty, it's interested in biomedical application. So we are doing that. And the climate change, and with the cosmological gravity wave, and even get into some of the financial data analysis. These are all current applications that we want. And I hope in this course I can touch upon some of the subjects of the application rather than just talk about the methodologies. Okay? So this introduction should end last time, but for some reason I probably becomes too talkative. I did not finish that. So from now on, we're going to get into the details. The result, you will see, we do have problems, a lot of problems, and this problem is what we are working now, and we'll try to solve this problem. So the first, I'm sorry I did not, I didn't post this on the website. Last night I did a final change on this, and after the final change I tried to look for Mr. Huang, and he wasn't there. Of course it's already very late, and I tried to send an email, but my email breakdown, I cannot send it out. And luckily I did not send it out, and this morning I changed it again. So this after the class I'll give this to you, and you can post it on the website. Okay. This, now we'll talk about empirical mode decomposition, shifting. Since I give you the overall picture, some of the view graphs you have already seen. So we'll now talk about the details. So the goal of the data analysis is to define time scale or frequency, to define energy density, to define joint time frequency density. Yeah, this is this method's for. And in fact, if you want, you can also define probability structure of each component. You can even define whatever. To do this, we need the AM/FM decomposition. AM is the energy, FM is the frequency. Yeah, if we can decompose any data into AM and FM clearly, and that will be great. Then you can talk about energy, you can talk about the frequency. The FM part gives you frequency, the AM part gives you energy. Yeah. Can we do this to any data? Yeah. So this AM gives you local definition of energy, theta t gives you local frequency. If any data we can do this, that would be great. The problem is that it's not that easy. Even though many times when I wrote paper, I said I cannot apply Hilbert transformation directly because it has problem. I get a very severe criticism from the mathematicians. They say, what do you mean, Hilbert transformation? Hilbert transformation, no problem. It exists for LP class of functions. I know that. But the problem is that after you get the Hilbert transformation, after you find the local phase, can you take a differentiation of that and getting the instantaneous frequency? And that instantaneous frequency still has to make sense. It exists, of course. You take a derivative just like what Stephanie Hahn did, as I presented at the introduction. It doesn't make sense. Not only it doesn't make sense, you give Hilbert transformation bad names. Yeah. So Hilbert transformation only offers meaningful instantaneous frequency for IMF. This is one of the first things. This sentence is very hard for mathematicians to accept. What do you mean meaningful? Define meaningful. Yeah. The only way that we can define meaningful that the mathematician will accept is that the frequency has to be positive, non-negative frequency. That's not all, in fact. That's not all. However, that's enough for the mathematician. So frequency has to be positive. And based on that, I have seen at least a dozen papers written on that already. Yeah. Looking for the class of function that has positive frequencies. That is, of course, important. But that's not the kind of thing that we want. Yeah. What we want is to not look for that function. Because our data comes out, it's a discrete point. How do I know what kind of function property it has? sometimes I don't, right? So whether that function satisfy or not satisfy a given functional type, I don't know. But I do want to find out the scales, the frequency, the instantaneous energy. Now, instantaneous frequency has various different definitions. When we talk about the comparison with Wigner-Weil distribution with wavelet, we'll talk about that. Some people maintain that a data set will have only one value of instantaneous frequency at one particular instance. And is that reasonable? I don't think so. Yeah, I think a complicated data, for complicated data, there should be more than one independent component. And if you have more than one independent component, we should have more than one instantaneous frequency at that particular time. Yeah. That separates us from some of the people specifically talk about time frequency analysis. Here, I think I will make a digression. The term time frequency analysis, for some strange reasons that I have not found out, must be historical or whatever. Time frequency analysis right now in the data analysis community is reserved for Wigner-Weil distribution. And the other part is talk about wavelet. And it's interestingly that the time frequency people don't talk with wavelet people. Wavelet people don't talk with time frequency analysis people. Time frequency analysis, the big name in time frequency analysis was Leon Cohen. He wrote a book, a very nice book, called The Time Frequency Analysis. Very simple. That. When you open the book, you find the whole book is talk about Wigner-Weil distribution. And in Wigner-Weil distribution, you read the Wigner-Weil distribution. Wigner-Weil distribution actually is a Fourier analysis. If you read that book does not even has one word. The wavelet does not even appear once. The same token, if you pick up a wavelet book, you'll read it through. Most likely, you will not find one reference to Wigner-Weil distribution. They are sort of like it's more than our two hands. They will never meet. Yeah, and you may ask, so what if they meet? If they meet, it's spectacular. I have witnessed one of those occasions. In one of the meetings, there were Wigner-Weil people. Leon Cohen appeared at the conference. There were wavelet people represented by David Donahoe. I'm sorry. David Donahoe is a professor at the Stanford University. He and Ingrid Daubechi did so much for wavelet. Both of them were elected to the Academy of Science, U.S. Academy of Science in 1999, I think, 1999 or 1998. Yeah, they're very, very famous people. So they are doing wavelet, and the other hand is doing time frequency. When they meet together, they argue just on end. It's argue. Not only they argue very heatedly. Yeah. The chairman will have to step in and says, oh, okay, stop, let's call it the truth, okay? So they don't actually see each other's merit, yeah. To me, I have my point. I think both of them are arguing for nothing because I don't think any of their methods is any good anyway. But for complicated data, however, I don't believe you should find only one instantaneous frequency because they are very different. There are many independent components. So the decomposition, we should get that dependent component out. But that method has to be adaptive. Yeah. Now, the last one is that if we know frequency, if we transfer our data into frequency space, and that operation is very, very different. Our decomposition is not operated in frequency space. We operate in a time domain. And here is my simple answer to why Hilbert transformation is not enough. Yeah, even though mathematicians told us that the Hilbert transformation exists for function of LP class. Why it's not enough? Very simple examples. Yeah. I have two sine waves. Yeah. Sine one wave plus another wave. And see, these are two typical identical sine waves. If I just swap the magnitude, I will get the two different curves. Yeah. So let's talk about curve number one. Curve number one, how does it look like? It's look like this. The lower frequency wave is much bigger. The higher frequency wave is small. This is a simple wave. So what if I ask you, you want to separate this into AM, FM? Yeah, AM, FM. First you should find out the AM. AM is what? It's envelope. Draw envelope for this function. How can we draw envelope for this function? What is envelope? Envelope is the max connection of the maximum. We'll connect this maximum to that maximum to that maximum, or connect this maximum to that maximum to that maximum. Yeah. So it's very different, the connection of extrema. And as a result, most people tell us, actually most people using envelope are the double E people. Double E books, if you look at those people, they say that the envelope only exists for narrowband signal. This is not narrowband, so envelope doesn't make sense. Now, however, does Hilbert transformation exist for this? Of course, yeah. Why don't we just take a Hilbert transformation of this? And Hilbert transformation, if you do a Hilbert transformation, this is the real axis. This is a Hilbert transformation of the imaginary. This function has a very strange behavior. It just keep on doing a loop around. Yeah. Notice that each of this little loop, when you go through here, the phase will go increase and decrease, and it gives you a negative frequency. Yeah. All this loop will give you a problem when you try to compute instantaneous frequency. But the Hilbert transformation still exists, right? So it does exist. Now once it exists, then I can get the magnitude of Hilbert transformation. It should be the envelope. And what's the envelope? Envelope look like that. Yeah. So if for a very simple function, I draw an envelope like that, you say, well, gee, is that envelope? That doesn't look like an envelope. This envelope fluctuates up and down, up and down, up and down all the time. Yeah. For such a simple problem, I draw envelope, have a problem. And you say, all right, let's change that. So envelope are only the connection of the extremas. So envelope connection of extrema becomes this line. Yeah. And that is a retrace of the data. It's not useful either. So even though Hilbert transformation exists, even for this simple example, we cannot use Hilbert to find the amplitude. We cannot use that particular frequency to get the instantaneous frequency. If you take that instantaneous frequency and take a derivative, it's going all over the place. In the introduction, I have already told you this doesn't work. And so observation. None of the two envelopes seems to make sense, right? The Hilbert transformation, the Hilbert transform the amplitude oscillates too much. The line connect the local maximum is almost the data itself. Yeah. So it turned out that though the Hilbert transformation exists, simple Hilbert transformation and try to use that to analyze data doesn't make sense. So for envelope, the necessary condition makes sense is for IMF, for the definition that I have. It's not exact narrow band, but you cannot have extrema, more than one extrema over the same, between two zero crossings. So if you decompose, you get two components. These two components are the two constituent components that I put it in. 0.2 times sine t over 16 plus the large amplitude. And this, you compare this component with the original data. So this is the component we pull out. This is the original data. So they looks the same except the some of the n effects. And this is the second component compared with the data. So with that, then we will we will see that for each IMF, the envelope will make sense. Yeah, and that so for the complicated data, we have to decompose the data into IMF before we attempt AM/FM decomposition. Yeah. So to be able to determine the envelope is equivalent to AM/FM decomposition. Yeah. Now let's look at the data number 2. Data number 2, it's much more well behaved. It's just going up and down, up and down. As you see, this go up and down, up and down. This is the lower frequency is of smaller amplitude. The higher frequency is high amplitude. This seems to be very easy to define envelope. I can draw envelope like that, and this looks more narrow band even. Yeah, the number of extrema equal to the number of zero crossing, but it's not symmetric to the envelope is not symmetric, right? So if we look at this data and we look at its Hilbert transform, and this Hilbert transform, real and imaginary, does not has a little loop, but it's not at one particular track either. Yeah, and if you plot this, you have the same thing. The envelopes go up and down. Yeah, but if you connect the extrema, in this particular case, it starts to make sense now. So if you have data that is single extrema between two zero crossings, then the extrema connection as an envelope seems to make sense. So all the EMD that we did is trying to reduce data to that state. That's very simple. And simply illustrate with this method. So even for this well-behaved function, the amplitude from Hilbert transformation still does not serve as envelope very well. Yeah. The complication for more complicated data, there are many complications. So the empirical, in this particular case, the empirical envelope, I call the envelope I define as empirical envelope. I will do spline, I will do maximums, I will draw envelope that way, even if that envelope almost retrace the whole data, I will take that. Okay, so that is the envelope I define. But even define envelope, I will not immediately use that envelope as AM. When I use AM/FM, I have to put an additional condition. That function has to be IMF, satisfy the condition that I give IMF. So empirical decomposition, so mathematically, I think there are infinite many ways to decompose any function. Give me a function, I can decompose it anyway. Very different number of ways. In fact, you can define any basis, empirical orthogonal, even empirical orthonormal function. You can define. Start with any function. Start with x. I can between 0 and 1. I can find its orthonormal basis. there are infinite many ways to decompose data into a complete set of components. Yeah. Now, the one that give us more physical meaning are more significant. So which one give us meaning? We can decompose it into trigonometry function. We can decompose it into wavelet. Yeah. There are so many different wavelets. If you look at some of the wavelet book, you pick up any wavelet book, you find that there are hundreds, if not thousands, of different wavelets. They're all orthogonal. Yeah. Orthonormal. You can normalize it. So I think the one that gives us physical insight is more important to us as a scientist than as an engineer. Yeah. Why it has physical insights? The ones that the ones that has physical insights are the ones that is derived from the data. It's based on the data. It's not something that you added on. Yeah. Now, in general, the fewer the number of the decomposition, the more information that each component contains. This is information theory. Yeah. Like Fourier decomposition. If you give them n points data, you get what? One half n components. So 1,000 data points, you get 500 components. And these 500 components, each one, the information content is very limited. If you give 1,000 points to EMD, EMD says log 2 base n. That's the maximum number of components you got. Yeah. So our decomposition, later I will show you, is actually dyadic. The length scale increased by 2, and it's adaptive. So these are some of the properties. Now this is the data that I have already shown to you. Now we can go very fast here. Here's the data. Now first we define envelope. Envelope now is my definition of envelope is the connection of maxima. Okay. So the upper envelope looks like a retract of the data. It's fine. The lower envelope again looks like a retract of data. Again, fine. Okay. My definition of envelope, it's not a Hilbert transform envelope. It's the empirical envelope. The empirical envelope is the connection of points, extremas. Upper envelope is the connection of maximum. Lower envelope is the connection of minimum. And with that, we get the center line. And this center line, again, is important because that's my mean. Mean of upper and lower. But is that real the mean? It is the mean of upper and lower. But mean of the upper and lower, strictly speaking, is not a mean. It's the median. Halfway between maximum and minimum is the median. If you try to look for the mean, I tried to look for mean. I was not able to do it because mean involves integration. And I don't know when to start and when to end. So here, you have to realize this is one of the details. I keep on talking about the mean, but in fact, what I'm talking about is median. That's one of the, if you try to look carefully, that's the difference. Yeah. So this is the median. This is the median of the maximum minimum. Okay. That, as I said, once I move that coordinate to the mean, I move this wave down, move this up. But if you look at this data, you will see that by successfully move all the waves, yeah, I change the coordinate to a curvilinear coordinate. And that curvilinear coordinate has its consequences, like, for example, create extra extrema. And as I said, we can keep on doing this. We have already done this before, doing this, and this is the algorithm. That is x minus mean 1 equal to h1. This I called a proto-IMF. It's not an IMF, but it's the original form, the proto form, P-R-O-T-O, proto form. Yeah. Now, this, I keep on refine it until come to this place. And this place, if I write this expanded out, okay, x1, x minus m1 equal to h1. h1 minus h2, m2 equal to h2. What is h2? h2 equal to x minus m1 plus m2. Right? So you can keep on doing this. Essentially what you did was x minus m1 plus m2 plus da da da, m to the k. So each time that I do this envelope and mean and adjustment, I add an extra term to it. So all of this m's are the result of empirical envelopes. How I get that? I get that from spline. So spline is important. I'll later come back to tell you why, tell you a little bit more about the spline. So the spline is important here. Which spline you use is very, very important. Yeah. But it's not going to change the answer that we get dramatically, because the number of extrema is important too. Yeah. It will give us slightly different amplitude, but it will not change the zero crossing position very much. Yeah. So you can see that each component, the C1, which is K, HK is the data minus a whole bunch of sum of envelopes. So envelope, we have to know which envelope, what kind of envelope we use. Yeah. At the beginning, I use all kinds of spline to construct envelope. I start from the second power all the way to the seventh power. Yeah. Later, I will tell you why we finally settle down to that. So this is important. If you expand this out, you know that the envelope is of critical importance. And now, finally, we get this component. This component is called intrinsic mode function. Why I want that? I want that at least serve as a necessary condition for the Hilbert transformation to give me a sensible non-negative frequency. But this is only a necessary, it's not sufficient. Even if I have IMF, if you just say, aha, I get IMF, I should always have positive, not necessary, not sufficient, it's not enough. You still will have negative frequency. Yeah. And that, when we talk about instantaneous frequency, we'll get into the mathematical reasons, and we'll give you how we get around to that. And at that time, I will enjoy good Hilbert transformation. This, again, is a very loose language as far as mathematics is concerned. What do you mean good? I do not have strict definition. The reason I choose good is because I read one book about Lighthill. Lighthill once wrote a simple book called the Fourier analysis, generalized functions, and he called the generalized function good. A good function is a function that has a derivative of all order, so on and so forth. It's a very nice little book on Fourier analysis, in fact. Now, once I have that C1, then x minus C1 equal to R1. R1 minus C2 equal to R2, and so on and so forth. I get x minus sufficiency. This I've already talked about. Now I'm going to see what are these C's and what are these R's. If we expand it out, we find x minus C1 equal to R1. So C1 equal to x minus summation mj, right? The first order mean. So this R1, if you compare this, you find R1 actually is summation mj. But the residual is all from the envelope. all from spline. So other than the first component, the rest are actually working on the spline functions. Yeah, the spline is based on the data. I trace through the data, I get a spline. So R1 is summation of this. Not only that, if you use R1 minus C2 equal to R2, so C2 equal to R1 minus R2 equal R1 minus summation of its mean, the second tier mean. So the C2 is the first tier mean minus second tier mean. So in other words, from now on, from all the R's, they are all spline functions. We are now getting away from the data. We're dealing with spline. Okay. Why the spline still maintain some physical meaning of the data? Because that particular spline is going through the data and following the data, is derived from the data. That is where the adaptiveness comes in. Yeah. So once we start this, spline becomes my only thing. Yeah, it's just like once you did in other kind of decomposition, I decide to use trigonometry function. Trigonometry is the only thing I have to remember. I can forget about the data. Here is the spline is the only thing I can remember, and spline is the thing. Yeah, the spline because it follow the data, so I remember spline. So this actually give us, in fact, if you people talk about the data compression, and this gives us a way for data compression. So data compression use wavelet, data compression use Fourier, is because they can use the limited number of base function. They only say, okay, this is my wavelet. I use this wavelet to decompose this. I only have to remember the coefficient of the wavelets, different order of wavelets. Then you can reconstitute the picture. Here is the same thing. It's all spline. All I have, what the spline goes through the extrema. So all I have to remember is the position of the extrema. Then I don't have to remember anything. So the number of extrema compared with the total data is a subset. So once you give me the location of the extrema, I can reconstitute my IMF. The IMF, the sum of the IMF is the original data. So I get the original data. So the this spline gives me the equivalent of sine cosine. But this spline, however, it's not a sine cosine that works for every function. This spline is work for only that particular data set. Yeah. So we are working on spline function. So with that, the x equal to summation Cj equal to x minus summation this. You see, x, this is C1. C2 is mj minus m2j. And C3 is m2j minus m3j, and so on and so forth. So here's a positive term and negative term to cancel. Positive term, negative term to cancel. So that's how we cancel all the r's. So if you add summation Cj, if you add that summation Cj, everything cancel and finally get x. So you don't lose anything. No matter what decomposition, what spline you use, you will still get back to the x. This decomposition is always complete. You always get back to your original data set. Yeah. This is the first residual. And as we push a little bit, we keep on adjusting. Remember, at the beginning, this side, the envelope after the first round, the envelope is already very symmetric. So the adjustment is very little over here. But this side and this side the envelope, at the first round, the envelope is very asymmetric. So there's drastic change. You keep on pushing up and pushing down. So we have a lot of adjustment in here, a lot of adjustment in here. But the final adjustment come to this point. This point is that will go through most of the the waveforms that we got. So this actually is the decomposition. And this decomposition, if the original data, I go through that, I have 1, 2, 3, 4, 5, 6, 7 components. Yeah. This is the original data I get is around 400 points. So it's to log 2 is the upper limit. Yeah. And then I define frequency this way because I use stationary phase approximation. It's not exact, but the second order improvement is very, very small. So this happens to be the definition that the theoretical wave people, classical wave people use. So I settled this, and I prove it by a stationary phase. Stationary phase means that I take the C, I wrote C equal to EI theta. I do a Fourier transformation. A Fourier transformation gives me this value. Whatever that value is, I don't care. That value may be the spectrum, I don't care. But I ask, what is the major contribution from that? The major contribution come from the stationary phase, time derivative of the phase equal to 0. And there are many, many ways to define frequencies. Yeah. And when we talk about instantaneous frequency, we are going to talk about the different ways. So the Fourier analysis, wavelet, Wegener-Weil, even dynamic system that you can define Hamiltonian, and we have Tiger, we have a period between 0, and finally we have this HT analysis, the Hilbert transformation. Yeah. This, we define frequency as time derivative. This will give you a continuous function. All the others, this red part, operate only for IMF. If it's not IMF, it doesn't work. Okay. This will work for any function. This method will work for only function, every function. This is only through low-dimensional dynamic systems. So why we want to do the shifting? There are two effects of shifting. The first effect of shifting is eliminate riding waves. We cannot tolerate wave riding on large waves. In other words, between 0 crossings, we can only allow one extrema, either maximum or minimum 1. If you have 2, that means you have a wave there. And if you cannot just have 2, you most likely either 1 or 3. Right? So those extrema, we want to get rid of those riding waves. The second effect of this, it's very detrimental to us. That is, it's to make the envelope symmetric. And when you push the envelope to be symmetric, how can you push the envelope to be symmetric? You have to push the large value down, the small value up. Yeah. So that you actually try to make the envelope symmetric is you try to make the amplitude of the wave more and more uniform. Yeah. So the consequence is to make the amplitude very even. Because of that, we have a dilemma. So how many times you have to do this shifting? You do more times, the envelope becomes the envelope becomes perfect symmetric. That means when we get to perfect symmetric is when we have upper envelope all straight lines. Yeah. That's the only time that you get a perfect symmetry. The difference approaches 0. All the other time, the difference most likely is not exact 0. Yeah. So, and when you push that all the envelope to be exact 0, then we'll have problem, because then we get only a FM function. AM is not there anymore. So here we have to judiciously think of a way when to stop, right? So, another thing is that there are singular points for instantaneous frequency. The singular point is that if we have theta equal to arctangent y over x, you take omega as dt d theta, you find that when envelope becomes 0, you have a singularity. X can be 0, y can be 0, but not amplitude equals 0. And in a few occasions, you do have envelope equal to 0, and that's the place that you have problem. Now, envelope equal to 0. Not only envelope equal to 0, when envelope is small enough, it starts to give you a problem. Yeah. So that's one of the places that we have to pay attention. We have to try to avoid too. So so in the operation, this is the operation that I use at the beginning. Now I think on the web that the shifting algorithm that we post is not EMD anymore. Yeah, I'm trying to. Here I'm presenting you the EMD, and eventually get to ensemble EMD. EMD. When we first developed this, we have many conditions that we set on EMD. The first is the big N, capital N. What are the maximum number of shifting we allow? We set a criteria this when we develop it, because this N is important. When we try different kind of spline, sometimes we get into a loop. It will never stop. And for certain spline, it does not converge. Especially when you have a higher order spline, it will never converge. Yeah, I will tell you why it will never converge. In other words, you keep on shifting. The more you're shifting, the more component you got. Yeah, and the scale does not reduce. The scale actually increase. So that's called Range phenomena. Yeah, the criteria for accepting a shifted component as IMF is the stoppage criteria. The stoppage criteria, we have different kind of stoppage criteria. I give you the Gaussian. Let me see whether I have that Gaussian or not. Yeah, there are two stoppage criteria that I use. This is more mathematically orientated. So for this, I can formulate a mathematical statement. I said, given epsilon, I'll find a capital N. Yeah, that epsilon is that if the difference between the two neighboring prototype are so small, I will stop. Then I can always find a capital N that within that capital N is finite. That statement, however, has not been proved yet. If we prove that, then prove that analytically, that's the convergence proof. Yeah, I have posted this to later. I will write that down in mathematical language. Give me epsilon, give me epsilon, I can always find a capital N. That by shifting capital N times, my difference will be less than epsilon. If we can prove that statement, then we prove the convergence. I haven't been able to prove that statement yet. What the proof is, empirically. Every time I tried, it never exceeded. It always stopped. Yeah, I have not seen anyone that's not stopping. And is that a proof? That's not a proof. That's not a mathematical proof. And that's one of the problems I pose to the mathematicians. And I pose to Ingrid Daubechies. I said, listen, if you can prove this, then convergence done. Yeah. Right now, every time I'm done, give me whatever data. I always finish decomposition in finite steps. Always. Using my algorithm. But I cannot prove that I can always do it. And that is important because if you change the spline, there's no guarantee that you can stop in finite step. We actually use the fifth order and actually it's blow up. Even if I use a third order, if I use a different form, it would blow up. I mean, the computer just keep running. It will never stop. Get into loop. It will never stop. Yeah. So this is the one of the stoppage criteria. The various form of this, you can have a different form. You can say that given epsilon, I can always have the upper and lower envelope. The mean of that is smaller than epsilon everywhere. That means that the center line is almost a zero line. That criteria is useful too. And that should be added. For example, if you want to use that, that's fine. In fact, the French people use that stoppage criteria. All of those criteria are mathematically fine. Yeah, I can make the difference small, either the upper and lower envelope or the one component after the next. But that only say that the difference between the two trial is small. Whether after the small, whether that function immediately satisfy the definition of IMF or not, is not known. So when I did at the beginning of the development, I insist on the fact that the component come out has to be IMF. How can I guarantee that? I give IMF a definition. The definition is the extrema and the zero crossing number has to equal. So every time after I've done this upper and lower envelope, I count extremas. Okay, how many extrema I get, how many zero crossing I got, I compare the two. If the two are within one, difference within one, I count it as, oh, at least I have that. Okay, so this is count of the zero crossing and the extrema. This and the others is counting the zero lines, whether the zero lines. So even when these two are not one for the other, but they're emphasizing different directions. In fact, both work very well because we don't have a rigorous proof. The empirical proof both work well. And this S number, that means I count zero crossings. And zero crossing and extrema, if they equal, I say, well, this satisfies the definition. But am I just lucky? Okay, I will do another shift. I will count the zero crossing and extrema, see whether they are equal. And if it's still equal, I will count the third times. So this S number is the number of times, that consecutive times, zero crossing and extrema equal. Not only they're equal the same number. Like if I shifted once, I get, say, 102 extrema. The second time, I also get 102. Third time, I also get 102. And the extrema and zero crossing are all 102. For 3 consecutive times, that's the S number equals 3. Then I stop. Okay. The other time, so I counted they're equal. The first time is 102. The second time is 103. The third time is 105. This doesn't count. So it has to be consecutively number of shifting. They are not only the extrema and zero crossing equal, but they are also equal to the same number. So this is a very, very strict condition that actually going back to the definition of IMF. This does not have anything to do with the definition. But the variation of this is the upper and lower extrema, the mean is zero. And that is the definition, is another part of the definition of IMF. So all of this stoppage criteria has been used by various people. I have used this for the beginning 7 or 8 years. I've been using that criteria. And even to this day, I still use it in many of the problems. But there are slight problem of using this. That is, each time the shifting are not the same number. Like the first couple components have to shift 100 times, maybe 60 times. The last couple components, twice is enough, or 3 times is enough. So there are none of the stoppage criteria is actually mathematically proof. Every one of the stoppage criteria used by various people are working pretty good. See, that's the loose end. This is the part that we have to tighten up if we have a good mathematician and you can give us some very, very rigorous proof of the stoppage criteria. Okay. We have 5 more minutes. We'll talk about the curvature shifting. What is curvature shifting? Curvature shifting is that now our shifting is strictly based on maximum minimum. We connect maximum, connect maximum. How about some hidden scales? That is a wave that has a maximum and a inflection point and a minimum. The inflection point does not present itself as maximum, but is there a scale hidden in it? Yeah. Mathematically, what we state is this. See, like data here. Is this a scale? Is this a wave? Is that a wave? And luckily, is this a wave? Luckily, through a number of shifting, we're able to pull this out. We're able to pull this out. But we're never able to pull that out. Is that a scale? We don't know. So we call that hidden scale. In fact, hidden scale, right now we use x prime equal to 0. Every point that is extrema, x prime equal to 0 is our controlling point, extrema. And not only that, x prime equal to 0, how about x double prime equals 0? How about x triple point equals 0? Once you take that maximum, and there are hidden fluctuation of the data everywhere. In fact, if we have xt, we can expand this into the value at that point, first derivative, second derivative, third derivative, and so on and so forth, all the way. So if we have all the derivatives at one point, we should be able to recover the whole function. If we have the derivative to the nth degree. Yeah. But to define this derivative, it becomes less and less local because define derivative is not at one point. You have to keep on expanding out, right? So how many derivatives should we stop here? If we go to curvature, we take the second derivative equal to 0. Yeah. Now, what we did is we actually calculated the curvature, radius curvature. We don't even stop at the calculated curvature. We want to find out the extremas of curvature. In fact, we already go to the third derivative. Find the maximum minimum of the curvature. And once you find the maximum minimum of the curvature, we put that maximum minimum together with the maximum minimum of the value and do a splice through that. And that immediately take away the first order of the hidden scales. Our justification of this extremal position is very simple. If x is position, this is a typo. If x is position, most of the time that the x represent the location of the point, then the first derivative is velocity, second derivative is acceleration. Yeah, physically beyond acceleration, we don't know what we'll talk about because Newton's law only stop at the acceleration. So I think that if we want to know the physics limited to the mechanics, the second derivative is what we can stop. So that's why we stop the second derivative. Okay. And if you want to go more, you can do it. But there's no guarantee that you will get the more meaning. In fact, even second derivative has some pitfalls, some shortcomings. If, for example, we do the Duffy pendulum. Duffy pendulum, if we use extrema, we can find the frequency modulation very nicely, and we can explain it. But if you go to the curvature shifting, the Duffy pendulum becomes two components. Yeah, one is the overall frequency. The other one is the modulation of frequency. Yeah, then you have to be ready to make an interpretation. As a result, I use this sparsely. We do have curvature shifting, but I don't use it routinely. I only use it when the data is extremely noisy. I try to get rid of the noise in the first one or two components. The rest of that, I typically use extrema shifting. Yeah. But the curvature shifting is there. It's available. It's sometimes useful if you find that the very small amplitude variation, you want to get it out. And curvature is the one that you can get it out. Okay? So we are 90 minutes from the beginning. I think our class in Japan will stop. So I will stop here. Is there any question? Are they still with us? Yeah. Any questions?
From here, they have no question.
No question. Thank you very much.
Yeah.
By the way,
Thank you.
by the way, this Friday, it's a holiday here. We will not meet. We don't have class. It's our national holiday. Yeah. So
Okay.
Friday, we don't have class. All right?
Yeah, okay.
Okay. Goodbye.
See you next Wednesday.
Yeah, sayonara.
Sayonara.
Goodbye. You have a nice weekend.
Yeah, thank you. Bye.
All right. Any question here? I'll stay a little bit longer here. Yeah. 有没有问题？我现在讲的这个啊，是把我们那个很detail的发展的历史都讲出来。因为你假如不走过这些弯弯路的话，你不会 appreciate 一个那个最后的 result 呀。所以我们要把这些里面的那些弯弯曲曲那个 detail 都讲出来。这个是我们这个 course 的这个 goal 呀。所以等到你学完这个以后，假如你们把这些东西都 digest 的话，你就 should know the inside and out of the EMD 跟 HHT。Any questions？ 有没有问题？用中文也可以问。没有问题啊？没有问题，我们就要下课了。礼拜五是双十节啊，没有课。OK， so everybody get it。我们这个课有个好处啊，日本放假我们也要放假，中国放假。好像11月初有一个日本的假期，是不是？ For some reason 11月初还有一个假 Well, we get whenever we have holiday, we'll not meet. But when Japanese side has holiday, we don't meet. So if we get more country to sign in, we won't have to meet any day. All right. 谢谢大家，拜拜。